Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on December 16, 2025, about 3 days ago. This paper introduces HyperVL, a multimodal large language model design for edge devices that cuts peak memory and avoids wasted vision compute with image tiling, an adaptive visual resolution compressor, and dual consistency learning for switching between small and large vision branches. The paper is titled HyperVL, an efficient and dynamic multimodal large language model for edge devices. Okay, and as we will see later, the on-device speed and efficiency gains look genuinely practical. Figure 1 makes the core claim concrete because it shows HyperVL landing unusually high performance for its size. The full scatter plot compares open compass average score against model parameters, with public models as circles and HyperVL as the star. The star sits around the 2 billion parameter region, but it scores like several larger 3 to 4 billion parameter models. The dashed curve hints at a general scaling trend, and HyperVL sits above that trend line. Figure 2 explains why HyperVL can run efficiently on a phone, because it makes the expensive vision work flexible. The full diagram shows a visual resolution compressor, which is a small module that decides how much to shrink an image so the model does not waste compute on unnecessary detail. The flow then branches into a base visual encoder or a large visual encoder, and both feed a shared vision language projector into the large language model decoder. The image partition panel shows tiling, which caps peak memory by processing big images in chunks. Table 1 pins down the exact model configurations, so the efficiency story has concrete parts. This table shows the full comparison area, listing model name, total parameters, the vision encoder choice, and the shared language model. HyperVL pairs SIG LIP2 base with QN31.7B, which keeps the system lighter. HyperVL swaps in SIG LIP2 large, which raises capacity while keeping the same language backbone. Figure 3 shows how the visual resolution compressor learns to pick the smallest image resolution that still preserves answer quality, so the system saves compute without losing much accuracy. The top panel builds training labels by resizing each image many ways and scoring them with cross-entropy loss, which is a measure of how surprised the model is by the correct answer. The selection block then chooses the best compression ratio under a loss threshold. The bottom panel shows Inference, where the compressor predicts a ratio before the vision language model runs. Table 3 shows that the efficiency tricks still translate into strong benchmark scores, even at about 2 billion parameters. The table body summarizes results across 4 domains, and the rightmost columns report HyperVL and HyperVL. The open compass average for HyperVL is 64.5, which stays competitive with several larger models. The OCR chart and document block stands out because DOCVQA hits 91.3 for HyperVL. Figure 5 shows that the on-device win is mostly about stable scaling, not just a small constant speedup. The full figure has 2 bars charts that compare QN3VL2B against HyperVL and HyperVL across increasing image blocks. The left panel shows memory staying nearly flat for HyperVL, while QN3VL2B climbs sharply as blocks increase. The right panel shows latency rising much more slowly for HyperVL, which supports real-time use at higher resolutions. Alright, 2 takeaways stand out. HyperVL makes on-device multimodal models practical by capping memory with tiling and cutting wasted vision compute with an adaptive visual resolution compressor, and it keeps quality high by aligning small and large vision branches through dual consistency learning. The broader implication is that efficiency can be dynamic and content-aware, not just smaller models. That is it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.